All right. So, can you guys hear me in back? I thought there was some thought that you couldn't be heard. I couldn't be heard in back. Very good. Okay. So far I did the startup transient analysis, and I optimized the loop response from doing the startup transient analysis. But in fact, from the startup transient analysis, if you look at the waveforms of the switcher during startup, you can find out all of the characteristics of the controller from the startup process. And I'll show you how to do that for this example of the 1624. Let's start by looking at the inductor current. Okay, so that's the current in the inductor, and I showed the inductor current before in the interest of finding whether or not the output voltage ripple was switching ripple or some other problem. So let's look at this inductor current again. So this is the switching frequency. You can see it switching up and down. And there's something interesting you can see here. This part is advertised to be constant frequency. And constant frequency is a desirable characteristic for a switchboard power supply to have. Because, you know, if you're going to use a switchboard power supply just to improve the efficiency of your power conversion, you would like to be able to pick what frequency it switches at and keep switching at that frequency so you can schedule that frequency to be some frequency that won't interfere with your system. So constant frequency is desirable, and this is advertised to be constant frequency, but when you look at the startup transient analysis, you see that it may well be advertised as constant frequency, but it, in fact, is not constant frequency, because when you first turn this power supply on, you'll see that it is switching at the wrong frequency, at a much lower frequency. Okay? Now, that low frequency behavior here, that's actually a desirable characteristic of the switcher. That characteristic is frequency foldback. That's the strategy that this controller implements in the interest of self-preservation in the event of an accidental fault short circuit to ground. If the output is accidentally connected to ground, this controller does not fold back the current, it instead folds back the frequency. Now, to understand why frequency foldback is an effective strategy for the this effective way of preventing the thing from blowing up, being damaged if the power supply is shorted to ground, you need to understand that this is a current mode switcher. Now, switch mode power supplies, there's different ways of categorizing switch mode power supplies. One way of categorizing them is by the topology. The topology would be whether it's a buck, a juke, a septic, a zeta, a flyback, forward, and so on. That's the topology. That's the arrangement of switches and inductors. But a different way of categorizing the switchboard power supply, categorizing switchboard power supplies, is by the mode of switch control. And there are two modes, voltage mode and current mode. Now, voltage mode is the older method. It was used in the 1970s. And to understand current mode control, or to understand voltage mode control, a voltage mode controller is basically a glorified comparator. So here's our comparator, and that's basically our controller. That is what controls the switch. Let me instance this up with a buck controller. Here's the in, there's the inductor, here's the output. Okay, so in a buck controller, you have an inductor connected to the output. The other side of the inductor is alternatively connected to the input or to the ground. One of these two switches conducts, and the ratio of time the inductor spends connected to one rail or the other determines the voltage bucking ratio. All right, now this thing, to regulate the output voltage, the output is sensed with a resistive divider. And a divided version of the output is compared to a reference voltage. The difference between the divided version of the output and the reference voltage, that is the error voltage, and the error voltage is amplified by an error amplifier. Now, for error amplifiers, I'm only going to use transconductance amps for error amplifiers. I won't use an op amp. I won't use op amps, but a transconductance amp. A transconductance amplifier amplifies an error voltage to a current. Okay, now the reason for doing that is because this is just a better way of doing it. Okay, you can think of this as an op amp without the output buffer. Okay, the output buffer, what it does is it buffers the voltage. You can drive some unknown low impedance, but I don't have to drive some unknown low impedance, so I don't need the voltage buffer. And the voltage buffer is the lowest frequency part of the whole op amp. So if I just don't print these output buffer, I get a part that works better, and I print fewer transistors. It's all win-win. So I only use transconductance amps. The output is a current, and I read out the current with a compensation network to a voltage. This is now an amplified version of the error voltage. That goes into one side of the comparator. Into the other side of the comparator, I put a high-frequency triangular wave. And these three component values are chosen such that this voltage changes very slowly compared to the frequency of this triangular wave. So the comparator is comparing a DC level to this triangular wave. The output is a duty cycle, and the duty cycle is adjusted to give you the correct output voltage. That is the basic convention of a switchboard power supply, and that was the method used in the 1970s. In 1978, current mode was invented. Current mode is a vastly superior way of operating a switchboard power supply. Whereas voltage mode is a glorified comparator, current mode is a glorified flip-flop. So here we have a flip-flop, set, reset, and output. And that is what controls the switch. Again, I'll instance this up as a buck controller. The output voltage is sensed with a resistive divider. The divided version of the output is compared to an error voltage, to a reference voltage. That's not good. The difference between these two is the error voltage amplified by an error amplifier, and again, the amplified current is read out to a voltage with a resistive divider. So I again have an amplified version of the error voltage. So from there over, it looks the same as this. The only difference is that's a flip-flop, and that's a comparator. That's the only difference. Now, how is this? What signals are given to this flip-flop to control the input signals? Okay, the flip-flop is set with a clock, and the clock puts out short little pulses here. Okay, and when a clock cycle starts, the clock pulse comes in, sets the flop, the output goes true, and this switch is turned on. And then the inductor is connected between the input and the output, and it just sits that way with the flip-flop latched to true. Now, the flip-flop is reset once the inductor current ramps up to a value proportional to the voltage on the output of the error amplifier. So to do that, we sense the output current, we sense the inductor current, it goes into a current sense amplifier, and once this current ramps up to a value proportional to the voltage in the output of the error amplifier, we reset the flip-flop. That is current mode control. Now, and this method was invented in 1978. By the 1980s, it basically took over switchboard power supply design, and no one has looked back since. Now, just why current mode is better than voltage mode is something I'll get into in about half an hour. But all you need to know right now is that's a current mode controller. But however, to implement current mode control, you need to sense the inductor current. Now, there's lots of ways of sensing inductor current. This just uses the time-honored method of a current sense resistor. Okay, that's why it has this 33 milliohm current sense resistor. It gives a small fraction of a voltage drop for a full-scale current through the resistor. But there's other methods. Some controllers can actually use the MOSFET as the current sense resistor because the controller is controlling the MOSFET. The controller knows whether the MOSFET is on or off. All the controller would have to do is look at the voltage drop across the MOSFET when it knows that MOSFET is on, and it can infer the current from that. That's the zero R sense controllers. And yet other controllers can use the inductor as the current sense element. See, the inductor actually has ESR. So a equivalent circuit of the inductor would look more like this. Okay, so the equivalent circuit of this inductor is better described as an inductor with an ESR. This is unavoidable. Well, this, so you can, and then if you add components, actual surface mount components of another resistor and a capacitor around the inductor like this, and if you pick this RC time constant to equal this L over R time constant, this time constant of integration cancels this time constant of differentiation. And the waveform you get across the capacitor is the waveform that you would have had across the ESR had that ESR been a discrete lump constant. Okay, it's an important technique because you're taking a great big huge square wave and integrating it down to exactly the waveform you want. It's a great technique. I won't use it today, but if you ever actually do design switchboard power supplies for a living, it's one you'd want to know. That's current inductor sensing. That's the way it works. You have to know what the ESR of the inductor is and then pick these two. And if they're not matched that accurately, the whole thing actually still works too. It's a great technique. But anyway, we won't worry about that. This just uses a current sense resistor, the simplest way of doing it, conceptually the most simple way of doing sensing this thing. However, notice that the current sense resistor is, I put the current sense resistor is in series with the switch. See, the job of the current sense resistor is to sense the inductor current, but the current sense resistor is not in series with the inductor. It's in series with the switch. And that is a jolly good thing, because the only reason for sensing the inductor current is to know when to reset this flip-flop. Once you reset this flip-flop, you might as well use the switch to switch the current sense resistor out of the circuit, and so you don't put current through it anymore. That is, I'm sensing the current here instead of here. And in doing that, you only sense the current when you need to know, because the reason for sensing inductor current is so when you know when to reset that flip-flop. And that actually turns out really well. It increases the efficiency of your controller, because not only, see, the thing is that a buck controller, they're rated by how high of a voltage bucking ratio they can buck in one step. If you can have if you can buck more voltage ratio in one step, it's a better buck controller. And if you buck a high voltage ratio, that switch is off almost all of the time, so you're almost never putting current through the current sense resistor. It's a great technique. All right. So it's great that you have the current sense resistor here, but the consequence is while you're trying to measure this current, you're actually measuring that current, the current through the current sense resistor. And the difference between the two is this spike. This spike of current goes through the current sense resistor and it doesn't go through the inductor. Now what that spike of current is from, it's from the capacitance of the Schottky diode. When you turn this switch on, this node goes from just below ground to the input voltage. It's a huge change in voltage across the diode, and the diode has a lot of capacitance. So you get a huge displacement current through the Schottky diode. You notice the displacement current through the Schottky diode is a bigger current than the peak current you're trying to put through the inductor. Okay, because that Schottky diode has so much capacitance. In fact, the fact of the matter is the Schottky diode is the most capacitive thing in this whole circuit. Well, I mean, except for the output filter cap. But other than that, it's the most capacitive thing in the whole circuit. Anyway, so you get all this displacement. You get this many amps of displacement current, and that don't go through the inductor. Now the problem with that is, I mean, look, think about it. The whole algorithm of current mode control is you set a flip-flop, and then you wait for the inductor current to ramp up to this value, and then you reset the flip-flop. But if when you set the flop, you get a huge spike of current through it, this current is bigger than the current that you're looking for. So somehow you have to ignore that flip-flop, otherwise you turn the flip-flop off as soon as you turned it on. And now in the 80s, what we would do is we would put an RC filter in front of the current sense amp, and you can imagine in your mind that at this point of operation, yeah, if you could pick a time constant where the resultant waveform might look something like this, it would come back down, you could still measure the peak current, and you'd still have some bandwidth enough to make this thing kind of work. You could imagine that. And it might work at this point of operation, but say you didn't need that much peak current. Say you only needed that much peak current. Then, because the load didn't need as much current. I mean, if you're powering something besides a hair dryer, the amount of current that the load needs varies depending on what's happening in the product that's powering. And so then you'd need a very long time constant to make this pulse small compared to that much peak current. And that would give you a very long minimum on time, and that would give you very little dynamic range of duty cycle left to control the output current. That's not good. Anyway, this thing, you'll notice that in this circuit, there is no RC filter in front of the current sense amp. There's none there. It isn't necessary because instead of RC filtering, this controller implements high-speed blanking. That is the current sense amplifier is momentarily shorted to ground. So when one of these clock pulses comes in, it sets the flop and grounds the output of the current sense to amp. Okay, and the time it's shorted to ground depends on the width of this pulse. Okay, then you unblank this thing, and then you can monitor the inductor current. This width here, depending on which controller you're using, it might just be 100 nanoseconds. So to scale here, it would unblank the thing at this point. And that means you could quickly blank this thing and then monitor the current with a huge bandwidth, the many megahertz bandwidth to reset the flop at the right point. Basically, it's stuff like this. That's why you use controllers. You base your switch mode power supplies on dedicated controller ICs instead of 555 timers because they're deglitched with junk like this in it. This high-speed blanking is very effective for the spike because the spike is very well isolated in time and not frequency, so it works great for that. All right, so it's great you have this high-speed blanking, gives you a very short minimum on time, but that very short minimum on time still isn't zero. And it might be too long under some potential operation points of the controller. For example, if the output is shorted to ground, then when you turn this switch, if the output is connected to ground accidentally, then when you turn this switch on, the inductor is then connected between the input voltage and ground. That's the biggest voltage in this whole system, and it's straight across the inductor, and the current ramps very fast. And that minimum on time the current might overshoot the maximum allowed current through this minimum on time. And if the current goes through the inductor, also goes through that switch, then it could blow up that switch. That's where frequency foldback comes in. The controller looks to see if the output is shorted to ground. If the output is shorted to ground, it slows the frequency down, maybe by a factor of 100. And then that minimum on time is a much lower duty cycle, and you're much more likely to not overshoot the peak current because you've given the inductor current more time to ramp down before you start ramping up again. Okay, that's frequency foldback. And let me just say, I'm a really big fan of frequency. Okay, let me first show how frequency foldback is implemented in this. Okay, so the controller has to detect if the output is shorted to ground. If the output is shorted to ground, it goes into frequency foldback. And the way that's implemented is the feedback pin is driving two signal paths. One goes to the air amplifier, the normal feedback loop, and the other goes to the short circuit to ground detector. Now the short circuit to ground detector is a comparator. So the feedback pin is also driving a comparator, and that is the short circuit to ground detector. One side of the short circuit to ground detector comparator is the feedback pin voltage, which is a divided version of the output, and the other side of the short circuit to ground detector is a divided version of the reference. So this thing detects that the feedback pin voltage is too low by a factor of 3. If it is, then that fires the short circuit to ground detector and slows the switching frequency down by a factor of 100. Now, This might seem like a sloppy way of detecting short circuit ground. Think about it. It looks at the feedback pin voltage. It says, oh, the feedback pin voltage is too low, say by a factor of 3. Well, the feedback pin voltage is too low by a factor of 3. The output must be too low by a factor of 3. I bet it's shorted to ground. I'm going to go into short circuit protection mode. Seems sloppy. But the fact it works that way is a jolly good thing. Because think about what the problem is with this output being shorted to ground. If this is shorted to ground, you turn the switch on, you have this huge voltage across the inductor, and the current ramps very fast, and it might overshoot the peak allowed current through this switch over that minimum on time. But say the output isn't connected to ground. Say it's 1 volt. You still have this abnormally high voltage across the inductor, and still ramps very fast, and it might overshoot. See, the thing is, when the switch is turned on, the inductor is connected between the input and the output. If the output is low, abnormally low, you have an abnormally high voltage across the inductor, and that's when you want to go into frequency foldback. Okay. Anyway, that's the way it's implemented. That way it works. It's hard for me to describe how much of a fan I am of frequency foldback until I showed you just how it works into a short circuit. Let's try this into short circuit. Let's take this output, connect it straight to ground. There's the inductor current. Okay, so that's the inductor current with this thing running into a, indefinite short circuit, indefinite time short circuit. This goes up to 5 amps. Okay, peak current is 5 amps. That's the current limit. That means that this power supply will actually operate at current limit into a short circuit. And that is as good as it gets. Because if the output voltage is 5 amps, it seems dangerous to put that. So, and think about what I'm saying. I'm saying if you walk up to the switchboard power supply while it's running and you wrap a paper clip between its output terminals, the thing will operate at current limit into that short circuit. But say you actually did that, and you guys probably don't have to worry about this at this point in your life, but once you're working at a company, say you actually did that, and then you realize, oh, it's Thursday. It's my turn to pick up the kids from school. I gotta go. Then you go. And you come back to work Friday morning, and you look, that paper clip is still there. How's the rest of your day gonna go? Are you gonna have to call up your Analog Devices sales office and try to get a new demo board and say the dog ate the demo board or something? How's this gonna go? Well, let's look at the power dissipated in the switch. Okay, so to dissipate power dissipated in the switch, I take the mouse, I point at the switch, I hold down the Alt key. Okay, and that's the power dissipated in the switch. And I'll make this small enough to make sure you can see all the edges. Okay, it has these spikes. And these spikes of dissipation go up to 70 watts. Well, 70 watts is not a disco party. I mean, I've been calling these things power MOSFETs, right? They're not power MOSFETs. They're little tiny surface mount devices. I mean, you can't dissipate any power in these things. They're little tiny surface mount devices, and they don't have a heat sink. So 70 watts isn't going to be okay. But it doesn't dissipate 70 watts for very long. Let's see how long it dissipates 70 watts for. Let's zoom up on this thing. And what we want to do is we measure the width of these pulses. You can set up attached cursors and slide them around. It'll read out a difference. But, there's a much easier and quicker way of doing it. Let's say I just pretend like I'm going to zoom into this region. I'm going to pretend like I'm going to zoom into this region, and when I'm dragging this box around, down here the size of the box is read out. So if I position the size of the box, I'm pretending I'm going to zoom in. This dx, the distance from there to there, is read out down there as 3.7 nanoseconds. Well, that might be okay. I mean, yeah, it's 70 watts, but 4 nanoseconds. Maybe the transistor doesn't know it's dead yet, right? So what just happened is I plotted dissipation as a function of time, and I did not find out if it's too much dissipation. I found out that dissipation as a function of time is not what I am interested in. When people say dissipation, what they mean is average dissipation. Average dissipation is the physical quantity that powers a calorimeter. So to find the average dissipation, we have to integrate this waveform. But we're in luck, because the waveform viewer can integrate. And to integrate a quantity plotted, you point at the plot of the label of the quantity that you wish to integrate with the mouse, hold down the control key, left click, and that will tell you it is 38 milliwatts. And that's the miracle of frequency foldback. I can walk up to the switch mode power supply, wrap a paper clip between the output terminals. It will actually operate at current limit into that short circuit. In the top pass transistor runs cooler than under normal operation. That's why I'm a fan of frequency foldback. And yes, it runs at the wrong frequency. But, if your rail is low by a factor of 3, your system isn't running yet. So where your EMI products are sitting, you probably don't care. So that's why I'm a really big fan of frequency foldback. Okay. Let me plot this current again here. Let me go back to the original circuit here. All right, so there's the inductor current during startup. So the first thing I do, if I look at the first few switching cycles, since the output filter cap looks like a short circuit, I can tell what algorithm, if any, the controller implements for short circuit protection, because when you turn them on, they come up running in short circuit protection mode. All right, what else? Let me add one waveform to this. Let me plot the voltage on the output of the air amplifier. So this waveform here is that voltage. That's the voltage which in here is this voltage there. So I'm plotting that voltage and that current. Now, by comparing these two, I can see current mode operation. And current mode operation is you set a flip-flop, you set the flop, you wait for the inductor current to ramp up to a value, and then when the inductor current has ramped up to the right value, you reset the flip-flop. So you can see this envelope of peak inductor current is echoing the waveform of the output of the air amplifier. So you can see current mode operation by looking at those two waveforms. Good. But if you look very carefully at these two waveforms, you can see that that controller implements slope compensation. Now, what slope compensation is? Slope compensation is affixed to a grave problem in peak current mode control. See, the whole premise of this is that if I drive this flip-flop and operate it like this, what's happening is, since this voltage is controlling the peak current, since the average current is related to the peak current, what it means is that voltage is controlling the current. That's the premise behind current mode control. And why that's important is something I'll get into in about 25 minutes. Now, all right, the problem with that premise is it's not true at high duty cycles on a cycle-by-cycle basis. There's an ambiguity that leads to a subharmonic oscillation where this switch will be left on for too long, and the next cycle too short, too long, too short, too long, too short. This subharmonic oscillation is not desirable behavior from a switch mode power supply for two reasons. Okay, you've got this thing switching, and it means you're going to have EMI products, but now because of this subharmonic oscillation, you have EMI products at half the switching frequency, which is harder to filter because it takes larger reactances to filter lower frequencies. That's one problem, but that's usually not the main problem with it. The main problem with it is that in practice, the subharmonic oscillation is rich in stochastic noise, and that's a problem because of the nature of sidebands of FM modulation. See, FM modulated sidebands don't look anything like AM modulated sidebands. If you have a carrier, sine wave carrier, and you modulate it AM with a sine wave, you have sidebands that are simply sum and difference frequencies from Euler relations. That's good, great. But if you have a sine wave and modulate it with a sine wave, the sidebands the envelope of sidebands follow these Bessel functions, and they go on forever. But it's noisy, so you're not modulating it with a single frequency, you're actually modulating it with many frequencies. You simply have sidebands that are physically, that you have current not encrypted. See, in AM, the energy in the sidebands are near the carrier frequency. You might encode a kilohertz signal, but you don't have any kilohertz current in the inductor. It's all encoded on the carrier frequency. But at FM, if you have a kilohertz signal in, you can have kilohertz current in that sideband. The sidebands are physically, well, they go all the way through the audio frequency spectrum. And since the reactances are all piezo, well, I mean, the inductors are the capacitors are piezoelectric and the inductors are magnetostrictive. You'll hear this power supply make noise, right? Power supply should be seen and not heard, right? So it's not good. That's not, anyway, none of that's good. You don't want that to happen. Now the fix to this subharmonic oscillation is slope compensation. And slope compensation gets its name from the way that it is implemented. So here's the deal. If you do this, it's going to oscillate, so you can't do that. All right, now you're going to have this flip-flop. You're still going to set it with a clock, because if you don't just set it with a clock, it's going to run at the wrong frequency. You don't want that. So this is the set, what's connected to the S pin will be the same. Somehow we have to reset it by a different quantity. We'll just do it by a slightly different quantity. Instead of resetting it by inductor current, we'll modify it by a slightly different thing. The clock will put out two waveforms. One will be a slope function, which is where slope compensation gets its name. And we'll add some of that to the inductor waveform. So we'll take some of this signal and add it to the inductor current. So where the current ramps up, we'll add a ramp to it. And if we reset according to that quantity, you eliminate the ambiguity between peak current and average current on a cycle-by-cycle basis, and you get rid of the subharmonic oscillation. That's what slope compensation is. That's why it's done. And if you look at these two waveforms very carefully, you can see that that is exactly what the controller is doing. And the way you can tell that is by looking in this region here. See here, this is the voltage on the output of the air amplifier. It's simply at the positive rail because it's out of regulation. It says it needs more current. It's out of regulation. It's clipped at that voltage. So that voltage on the output of the air amplifier is a constant voltage. If this is a constant voltage, I should have a constant peak inductor current. But it's not constant. That is less peak inductor current than that. And that's because of slope compensation. And to see why you can see it in the sort of transient analysis, let me plot some more waveforms. And I'll plot pain. Let me also plot the input and output voltages. So here's the input, here's the output. When the top switch is on, the voltage across the inductor is connected between the input and the output when the top switch is on. The voltage across the inductor is the difference between these two waveforms. When you first turn the power supply on, the output voltage is 0. You have the full input voltage across the inductor. As the output voltage increases, you have less voltage across the inductor. And so to ramp up to the same peak current, you have to leave the switch on longer, which means you're resetting the flip-flop later in the switching cycle. If you switch on later in the switching cycle, you've added more of this to the inductor current. The fixed quantity will be the sum of this plus that. You have more of this, you have less of that. And that's why that's less peak inductor current than that. So one thing about the startup transient analysis is that sometimes it's the only way of seeing the slope compensation function of a controller. Now I drew here just a triangular wave for the slope compensation function. In fact, people who, we use proprietary slope compensation functions. They're not triangular waves. We can do better than just a triangular wave. And the people who make the IC designer who thinks of this proprietary function to build into his IC, when he writes the data sheet, he's enthralled with this slope compensation function, and he wants you to like it, he wants you to buy it, but he sure doesn't want to tell you what it is. So sometimes only by doing a startup transient analysis can you see what the slope, because the model has to have it. If the model doesn't have this thing right, the model's just wrong. There's no other way of looking at it. Sometimes the slope compensation function is the only way of seeing the, doing startup transient analysis is the only way of seeing the slope compensation function. I mean, literally, because during the startup transient analysis, the thing just runs over every duty cycle, you can just see how the thing behaves. I mean, literally anything you want to know about this controller is exposed during the startup transient analysis. And I'll just talk about something very simple. Okay. I've been calling this a controller because it controls that MOSFET. Let's talk about how it really does that. Notice that that's an N-channel MOSFET, which is good because N-channel MOSFETs are easier to buy than P-channel MOSFETs. There's a larger selection available. For a given die size, they have less on resistance. For a given price, they have less on resistance. Or for a given on resistance, it requires less gate charge to fully enhance the channel. We all know N-channel MOSFETs are better than P-channel MOSFETs. So it's great that this is an N-channel MOSFET. However, the N-channel is an inconvenient polarity in this circuit. See, this is the MOSFET that's used to connect the inductor to the input voltage rail. Well, when you do that, you want this switch fully turned on, because the whole idea of a switchboard power supply is that a switch can't dissipate power. You either have voltage or current, but never both. And so the whole idea is that when you turn this switch on, you want it fully turned on, because any voltage drop associated, the power associated with any voltage drop across the switch will be dissipated as heat in the switch, whereas the power associated with the voltage drop across the inductor, that power will be stored as energy in the flux of the inductor. So the whole idea of a switchboard power supply is you withstand voltage with an inductor instead of a switch. Great. So when this thing is on, it's fully turned on, which means that this node is at the input voltage. But to fully turn this thing, you have to pull the gate well above the source voltage to fully enhance the channel. And that, if the source is at the input voltage, that means that the gate has to be well above the input channel. And that's the problem. I mean, I got an unregulated 12 volt. I'm regulating to I'm converting to a regulated 5 volt rail. So I got unregulated 12 volt. I have regulated 5 volts available, but I need 18 volts from somewhere to turn on the MOSFET. And I don't have an 18 volt rail, and I don't want to have to buy my power supply a power supply. So when I just to describe how this problem is solved, let me first show how the circuit is implemented, and then I'll describe its operation. That'll be a much clearer way of going there. Okay, so there's a controller, and the controller has an integrated gate driver. And by integrated, I mean printed on the same piece of silicon. So there's a gate driver. And these are both mechanically printed on the same die. So this is 1624. All right, the controller, needs some power. And it has this thing printed on the same silicon. Now, despite the fact that the gate driver is printed on the same silicon as the controller, the gate driver is floating. It's not connected to ground. Now, think of the gate driver as a 4-terminal device. Input, output, power, ground. 4-terminal device. The input is connected to the controller. This particular one, the connection is not bonded out. And since you don't know what potential this thing is at, let's assume it's differential. Okay, the other 3 pins are bonded out as pins. And that's exactly what those pins do. It would be more clear if they were labeling those pins than what they are. Okay, so the output of the gate driver is the pin. Okay, the output of the gate driver goes to the gate. Okay, the ground connection of the pin driver is the pin called switch. It has this pin called switch. I mean, you don't really want a pin called switch. You want to buy an IC, you want to apply power, connect the gate to it, and have it switch and have it drive the gate right. That's all you're really interested in. You don't want a pin called switch. But the switch pin is the ground connection of the floating gate driver. Okay? That's what it does. And it also, now the positive supply of the gate driver is the pin called boost. You have no interest in a pin called boost, but the boost pin is the positive supply of the floating gate driver. And now you see what C1 does. C1 bypasses the power supply for the floating gate driver. Okay, that's what it's doing. Now, the normal situation with controllers, I mean, there's thousands of controller products on the market. Most have floating gate drivers, integrated floating gate drivers. And usually the gate driver is printed on the same silicon as the controller, but it's floating and it's not powered. You have to power it from someplace. This particular product is an exception to the rule, and that the boost pin power does come from VN. The circuit that connects them is an LDO, a 3-terminal regulator, a low dropout regulator, followed by a diode. That's the implementation of inside. Now we'll describe its operation. When this switch is turned off, the source is just below ground. It's held there by the Schottky diode. That means that for C1, this end of the end of C1 is held just below ground, and this end of a pin connected to boost, that diode is conducting, and the boost pin is connected to the LDO output of Vn, so it's at Vn. Okay? Now, when the controller tells the gate driver to pull this thing high, you still have current flowing through the LDO and the diode, but eventually it'll start enhancing the channel. And then, when you start enhancing the channel, this node will start slewing positive, and this pin will bootstrap the boost pin with it. So we can watch this, we can look at these waveforms. There's the boost pin voltage. Here's the, here's the input voltage, and you can see the boost pin voltage is biased well above the input. Well, I'll tell you what, let's do differential cross probing. Let's look at the gate source voltage. Let me add a plot pane. This is differentially probing gate source voltage. That's the gate source voltage. You see it goes 0 to 5.5 volts. So that's, if you want to know what this control is exposed during the startup transit analysis. By the way, all the MOSFETs of these things are logic level MOSFETs. You know, we used to have high voltage MOSFETs. These are all logic level MOSFETs when you control it. That's the idea there. Okay. Was that fun? I'm finally done with startup transit analysis. All right. Let's review. It's the world's fastest SPICE. That is, you give the same simulation to LT-SPICE, the same netlist to another simulator, LT-SPICE will win. It's the most accurate SPICE. It's the most numerically robust. And it's free. You can simulate anything you can draft, unlimited node count, unlimited component count. You can plot anything you can point at. You can plot anything you can type. It's free. And it has all these controller models. There's thousands of controller models, about close to over 1,000 controller models in LT-SPICE. Basically, on the planet, there's only so many controller models that have ever been done. Almost every single one of those are in LT-SPICE. You know, there might be 100 or 200 outside of LT-SPICE. So, you know, if as a sloppy manner of speaking, you choose to say that if a switchboard power supply controller model exists, well, that's a model of an analog devices product, and it's in LT-SPICE. You know, if you'd said that, you'd be wrong. But your error is down 20 dB. Okay, I mean, those models are the prize of LT-SPICE. They actually incorporate more source code than the simulator itself. Okay, those models are all free. So, now all of that, for a few people, for some people, that's enough. I mean, they're ready to get involved with LT-SPICE. They're in the car, all right? But all of that is not enough to make LT-SPICE actually useful in real life. And I'll show you why it's not enough. It's very simple to illustrate. So after you get done listening to me, you go home, you install LT-SPICE and say, yes, I know how this works. I push this button here and I get a blank schematic, and then you look at that blank schematic and then you ask yourself, what did that guy do next? See, that's the problem. For this thing to actually be useful in real life, there have to be support resources to go along with it. All right? So let me outline those support resources. First of all, I'm perfectly aware that engineers do not like to ask questions, so there's thousands of examples. You install the thing under your documents directory, LT-SPICE 17, examples. There's two subdirectories, examples educational, examples jigs. The examples educational directory is a collection of non-commercial examples that simply show you how to do SPICE simulations. Some of them are very simple, like there's one called curve trace, okay? It only has 3 components in the whole simulation. It shows you how to extract the output characteristics of a transistor. It's just there so you can see how to curve trace a transistor. There's a simulation called noise figure. It It's a very simple transistor amplifier. It shows how to set up a stochastic noise simulation, and there's comments on the schematic that tells you what quantity to plot, so you can plot noise figure versus frequency. That's the point of it. There's LT-Spice is a mixed mode simulator, which means, among other things, you can draft with gates and flops. Here's the register level schematic of a 74-160 decade counter, and you can watch it count to 10 in BCD. Okay. There's a few IC schematics. This is a 555 timer, a transistor level. You can simulate this IC. You can plot every device current and node on the whole IC. Okay, and there's a few IC schematics, various industry legacy ICs, like a 741 op amp, a 308 op amp, 555, and a 1648 VCO. And there's this thing here. This is the P2. The P2 is kind of interesting because the P2 was the first solid-state op amp. It was from George A. Philbrick. Now the thing is, actually, let me talk a little bit first about George A. Philbrick Researches. George A. Philbrick had a company that he called George A. Philbrick Researches. Don't never name a company after yourself. You can never sell it. But anyway, just a heads up, all right? Now, George A. Philbrick created the op-amp market. I mean, the very idea that a commercially viable product would be an electronic amplifier that had so much gain, it was useless. I mean, an amplifier that would amplify its own offset voltage so that the output was just stuck at one rail or the other, that's a product that people will pay for. That idea is due to George A. Philbrick. He says, well, people put a resistive divider around this thing to program the gain with feedback. Okay, now, George A. Philbrick, he created this market. He implemented vacuum tubes. He implemented op-amps implemented with vacuum tubes. In the 1950s, he sold op-amps made out of vacuum tubes. He called what he was doing analog electronics. But it was all analog in the 50s, right? I mean, so why did he say he was doing analog electronics? Well, you know, unless you were doing, you know, cryptology for the government or something, all the electronics was analog. Well, he used the word analog differently than we do today. In fact, he had a whole different point of the whole thing. Today we use analog electronics basically because of his nomenclature, and we mean continuously varying. But he meant analog originally not to mean continuously varying. He meant it to be analogous to something else. Okay, so you would do in analog computers. Like he sold op amps to mechanical engineers. You have to think about the 1950s. I mean, who were the smart people in the 1950s? They were mechanical engineers. They were making rockets, jets, and cars. Okay, they were all the smart people. And he'd go up to a mechanical engineer and says, "Look, you guys are smart. See this? I call it an op amp. Don't worry, I sell them." But anyway, with this thing here, this thing's more accurate than a slide rule, and you can integrate differential equations. What you do with this is you make the electrical analog to your system, like, and I'll show you how to transcribe, you know, mechanical stuff to electrical component values. And then you optimize the component values so the circuit works right, the analogous circuit works right. Then you take those new values back to your mechanical system. Why? With this thing, what you can do, you can design an engine mount that's critically damped, so when your jet flies through the sound barrier, the engine won't fly off the wing. Now, obviously, if you're a mechanical engineer in the 1950s, you would have no defenses against that sales pitch. You'd be like, "Oh boy, how many of those can I buy?" You know, you'd want as many. You know, you'd have no defenses. You'd have to buy these things. He sold these things to op-amps. Okay, now the very first op-amp that was implemented in solid state that went to market was the P2, and that's the schematic of the P2. It was implemented with discrete transistors, discrete germanium transistors, on two printed circuit boards about this size stacked on top of each other. The way the thing worked was, okay, here's the differential input here, inverting input, non-inverting input. These inverting input signals would meander around to this varactor ring. this varactor ring was a mixer, parametric up conversion. See, the inverting input would come around to this node and that node. The non-inverting input would come to that node, and this varactor ring was pumped with this local oscillator. So if there was an input signal, you would get an output at the local oscillator frequency that would come out here, amplified by this IF strip, synchronous detection here, and a single transistor baseband gain. That was the way it was implemented. Now, because it was implemented that way, it had some very interesting performance characteristics. For one, because the input is only transformal coupled to the rest of the circuit, there is no DC conduction mechanism. So that means that the DC common mode rejection ratio was infinite and spanned hundreds of volts, whatever the transformers could isolate. Okay. Also, it required very little current, very low bias current. It doesn't take much current to imbalance a varactor ring, especially when that imbalanced signal is being driven back to zero with the full open loop gain of an op amp. So the bias current was exceedingly low, typically 10 picoamps. So it was really a breathtaking feat of electrical engineering that when most people are mucking around with vacuum tube circuits, George A. Philbrick, researches, has a solid state op amp that is a turnkey electrometer over vacuum tube voltages. It's really a stunning electrical feat of engineering. But that's actually not the most impressive thing about the circuit. The most impressive thing about this circuit is that it was monetarily breathtaking. He made an unbelievable amount of money off of this. So the thing is, and this circuit was designed in 1959, went to market in 1960. Now, in 1960, you could begin to buy a transistor radio, a little portable transistor radio. That transistor radio would have the same number of germanium transistors, almost the same number of germanium transistors, but the transistor radio had a lot more electronic components in it because of the tune coils and the knobs, the speaker, the box, the retail experience. This whole transistor radio commanded $11. You guys are really young. Okay, the United States was on the gold standard. Okay, that was 1/3 of an ounce of gold. You would have to stand in a river up to your knees a long time to get to pan 1/3 of an ounce of gold. Okay, it was a lot of money. This thing didn't sell for $11. It had half of the electronics, no particular retail experience. It sold for $188. That is almost half a pound of gold. And he couldn't make enough of them. He had to buy more buildings and expand. He had a whole factory making this thing. He had to buy more buildings. That's what's impressive about this circuit. Now you would expect that the next part of the story would be, and so that's when this other company came in, entered the market, and they second sourced the circuit for a cheaper price, for the good of mankind. Right? You'd expect that to be the next thing that happened. Never happened. No one was ever able to second source this circuit. It's because it had a little bit of unusual characteristics in the way it worked. Now, there were companies that tried to second source it. One company is documented as, they got the best, most recent PhD graduate they could get. They gave him some P2s, and they told him to generate document control instruments against which they could manufacture this thing. Okay, now he could get the schematic. It's not like they scraped the numbers off the transistors. He knew the schematic because he could get the schematic. He could scope the thing out. He was never able to duplicate it. He could prove it couldn't work, because he knew theory well enough that he knows the maximum theoretical gain you can get from a transistor, and there weren't enough transistors in this circuit to give the DC gain on the data sheet. It was not possible the circuit could work, and he could prove it. He could also measure that it did work. And that's because it had a little bit of an unusual aspect to it, and that is it used positive feedback to get that gain, positive feedback at the IF frequency. And I'm hypothesizing in this simulation that it was 50 femtofarad of stray capacitance from that stage of the IF to that part of the input. If you put that 50 femtofarad feedback there, the entire behavior of the P2 falls out. It has the right DC gain, the right gain bandwidth, the right slew rate bias. It works exactly like a P2, even down to the operation of the circuit over these two factory adjustment screws that were in the side of the P2. One factory adjustment screw was called offset. It adjusted a potentiometer and its operation was straightforward. But the other factory adjustment screw was called gain, and it adjusted a piston capacitor. And its job was to adjust the phase of the regeneration signal so this thing would operate with positive feedback robustly in the field. So I put that there. That's another, and you can simulate this thing, the world's first solid-state op-amp that went to market. Basically, an example is educational. Every single example is contrived to try to illustrate something. Every single one is tries to show how to do something, and they are literally my humble, flat-out, best effort basis to make you a SPICE expert. Okay, that's why they're there. So if you have some familiarity with LT SPICE and you want to know a little more familiarity with LT SPICE, look through the examples and examples educational and see if there's something there that's interesting to you and follow that. That's what I recommend people do. Okay? Now the other directory in examples education is called examples jigs. The jigs are the a jig is another word for fixture, as in test fixture. These are test fixtures for the macro models. Every single product for which Analog Devices distributes an LT SPICE model, we include an example simulation that you can immediately run the model in. Okay. For the op amps, these will be all the normal op amp circuits. Differential amps, instrumentation amps, active filters, preamps, so on, all the normal stuff. For the switchboard power supplies, they're all going to do startup transient analysis. And so you can immediately open up the jig circuit, poke the running man, and do a startup transient analysis. Now we'll say a little bit about this particular part because this is different than what I did in the demo. In the demo, I took a controller IC, attached a power MOSFET, and built up the parts and made a switchable power supply. This controller IC has an integrated power switch, so it's not controlling an extra switch. It's not a controller product. It's just a voltage regulator. But what's interesting here is that I still have this pin called boost. And the last time I showed you a pin called boost, I said that the boost pin was the positive supply for the floating gate driver for the external MOSFET. Well, there is no external MOSFET in this circuit. In fact, there's no internal MOSFET either. The switch is bipolar, so there's no gate driver, and it still has this pin called boost. Well, the boost pin is serving an analogous function. The thing is, okay, now, so we know it's a bipolar switch, and the switch connects the switch node to VN. The switch is connected between these two nodes, and it's bipolar. It's actually specifically an NPN transistor. It's not a PNP transistor. And the reason why it's NPN and not PNP is because NPN transistors are better than PNP transistors, just like N-channel MOSFETs are better than P-channel MOSFETs, and they're even better for the same reason. Electromobility is higher than hole mobility. So, it's an NPN transistor connects the switch node to VN. Using an NPN transistor, the collector is connected to VN and the emitter is connected to the switch node. For a PNP, it would be the other way around. But it's NPN with collector there and the emitter there. Now, when you turn that transistor on, you want to have as little voltage drop as possible across that transistor, which means you want that transistor to saturate. And the definition of saturation of a bipolar, of an NPN transistor is a transistor operated with the collector voltage below the base voltage. Since the collector is connected to the most positive voltage available, you again need a voltage bootstrapped above the input voltage. And you can, so here's the boost pin voltage, and there's the input voltage. You can see you can have a voltage going above the input voltage. There it is. Now, let me tell you, there's a couple of life lessons here. Say your life takes a path where you find yourself applying for a job designing switch mode power supplies. It can happen. Now, during your quest to get this job, you're probably going to have to go to some interviews. All right. All right. Now, during the interview, you can be confronted with a question along these lines. They shove a great big schematic in front of your face, and they demand that you identify the topology of a switcher. They can do that. Now, this is my first time in the Philippines. It's a flat out honor to be here, but I don't know labor law in the Philippines. Where I live in California, labor law is this highly developed, strange thing. And there's certain questions that you cannot ask in California during an interview. It's just illegal. For example, if you're interviewing a person in California, you cannot ask that person their age. That would be a clear sign of age discrimination. If you interview someone in California and you ask them their age, you could end up making your company and yourself personally liable for that person's entire wages and compensation for whatever short, miserable life that old person has. Okay, so you can't do that. But the topology of a switcher, you can ask that. All right, so the first thing is, when they show you that schematic, don't look for the switches. It's a trap. Because the switches might not be drafted. The switches might be integrated in some of the controller ICs they're using, and there you see why they've asked you that question. They just want to see if you know what commercial products have integrated power switches and which ones don't. And they're just asking you that question out of some selfish interest of their own to see if you actually know anything about switch mode power supplies. Well, you might not know anything about switch mode power supplies, but you still want the job, all right? So don't look for the switches. Look for the inductors. You've got to draft the inductors. That's the first life lesson. The second life lesson here is, if the biggest thing on that schematic is an integrated circuit with a pin called boost, it's a buck regulator. Because buck regulators typically use an N-polarity switch for the high side, and it will usually need a voltage bootstrapped above the input. So as long as you remember that buck regulators use an IC with a pin called boost, and boost regulators don't have an IC with a pin called buck, you'll probably be okay. But honestly, quite frankly, most switch mode power supplies are bucks. And so if the answer isn't, oh, it's a buck regulator, it was a trick question. This is what life is, okay? All right. Now, the jig circuits can be a useful starting point for an actual thing you might actually want to put into your system and, and get on with life. And this is an example that shows where they can be very helpful. You got this, this is a 3733, it's a three-phase switcher, it's a polyphase switcher. What a polyphase switcher is, it's a switch mode power supply still with a single input and a single output, and in between the input and output are multiple power supplies sharing the current. Now the point of sharing the current among multiple phases is not really so much to get more current through the switcher. I mean, if you have a switch mode power supply and you just want more current, you should first consider using larger MOSFETs. It's much more direct. But the reason for divvying the current among multiple phases is that you can stagger the inductor ripple current phases so that when they sum on the output, the ripple will diffract. They'll destructively interfere, and you can make a switch mode power supply with a very low net output ripple. Depending on the number of phases and the voltage ratio between the input and output, they can precisely cancel. And then you'll have no current going through your output filter capacitor, so there's nothing flowing through its ESR dissipating power, and you have nothing read out to a voltage. That's a polyphase switcher. Now this part here, each IC will control three phases, but you can daisy chain these things with PLLs and all that and run lots more phases. But just to look at one of these polyphase switchers, okay, there's three phases, so there's three inductors, there's three current sense resistors. Each current sense resistor voltage has to be hooked up to the right current sense amp. It supports synchronous rectification, so there's 2 MOSFETs per phase. The thing supports remote voltage sensing. That is, there is an op-amp printed on the same silicon as the controller to support remote voltage sensing. And you have to hook up its feedback network, and there's no option not to use the op-amp. You have to hook up that op-amp to evaluate the power, try the thing out. There's still an error amplifier in its compensation network. There's a DAC to program the output voltage. What I'm getting at is that this is just a lot of stuff to draft to do it before you can do your very first startup transit analysis. And you know how these things are. You get one wire in the wrong place, the whole thing doesn't work. And it doesn't tell you why it doesn't work. So that's the value of the jig circuit. You can open up the jig circuit, you can poke the running man, immediately do a startup transient analysis, look at those waveforms, and decide whether or not you want to spend any more time with that controller or not. That's what they will do for you. However, the jig circuits are not reference designs, okay? The jig circuits are made to quickly show you the behavior of the controller, but they're not reference designs because they're made to simulate fast, not be good circuits. Now, there's usually an error in the circuit that makes it simulate very fast, but makes it also entirely impractical. But what's done here is the soft start cap is very small. Now, a current mode controller doesn't actually need a soft start. It can just work at its own current limit, be happy, and start up. But the only trouble is it's going to charge up the output filter output filter bank at current limit, which means it's drawing a huge current from its input just to charge up the output filter cap, which is rude, right? You'd like to, maybe take 10 milliseconds to charge up the output filter bank, so you don't draw a huge current from the input just to charge up the output filter cap. Okay, so this soft start cap is tiny. It goes through soft start in 100 microseconds, where 10 milliseconds would be a more reasonable soft start time. So basically, to convert a jig circuit to a reference design, you have to audit the value of the capacitances in the circuit. You have to find the one that probably is too low in value. It would be the soft start cap is too small. And there is one capacitor that is required that is missing. And the capacitor that is missing is the input filter cap. See, you have to bypass, you don't just need an output filter cap. You don't just need this capacitor here. You have to filter the input. Otherwise, the ripple in the inductor will travel all the way down to the harness wiring or PC board traces to that thing, and you don't want that RF going down there. You want all the RF. You want DC in and DC out. You don't want a DC in and RF out the input and just DC out the output. You have to filter. You have to bypass the input filter. Now, the reason why I don't put an input filter there is twofold. One is I'm using a voltage source, and since the voltage source has no impedance, if I were to put a capacitor there, it would just be a decoration. There wouldn't actually be any current in it. So as a matter of intellectual honesty, I leave the input filter out because it's not actually doing anything. But there's another point there which is maybe more interesting, and that is that when you make a current mode controller, the input filter cap has nothing to do with the design of the controller. Let me explain what's happening. All right, see, in this circuit, the reason why this filter capacitor here only decouples this circuit from the rest of the system. It's not part of the design of the circuit. The reason why it's not part of the design of the circuit is because this circuit has an essentially infinite line rejection. Line rejection is how much output changes you get for input change. So the thing is, say this input voltage here goes from 12 volts to 10 volts and it goes in 1 nanosecond. What's the change in the output voltage? Well, 0, of course, because this flip-flop stays on long enough for the peak current to ramp up to a fixed current. It just, whatever duty cycle is necessary to ramp up to that peak current is how long this switch stays on. Then it disconnects the switch and it just reads out that energy in the inductor. It just this dot current conducts. So this circuit is only integrating the volt seconds across the inductor to ramp up the desired peak current. What waveform was across those volt seconds, during those volt seconds, doesn't make any difference. This thing has infinite line rejection to a first approximation. That's not the story in voltage mode. In this thing, if you get abrupt change in voltage here, You have to change the duty cycle, which means you have to change this voltage, which means you have to slew the voltage on the compensation capacitor. And that can take milliseconds. See, on this compensation capacitor, you just have a voltage there. It says how much peak current you have. Let the flip-flop figure out the duty cycle. You don't have to change the voltage on this capacitor for that. Anyway, I have a little example here that you might find interesting. So here, that is this circuit. This circuit is that circuit. That's a voltage mode controller. There's the comparator. This circuit is that circuit. That's the flip-flop. And I'm going to hook them both to the same input, and I'll have the input voltage step from 8.5 volts to 15.5 volts. Let's see what the output voltage does. So here's the input going from 15.5 to 18.5 volts. And here's the two outputs. Output V1 is voltage mode. You can see the perturbation of the circuit, where the current mode controller doesn't change at all. To make this even more clear, let's look at the compensation node voltages. Those are the compensation node voltage of the voltage mode amp. You have to, that has to change. But if you look at the compensating voltage of the current mode controller, no, it doesn't have to change at all. Just the specifics of the ripple changes a little bit. So that's one of the advantage of voltage mode versus current mode, is that a current mode controller has, through first approximation, infinite line rejection, where a voltage mode controller has zero line rejection. Okay. Now, I was going through the, okay, great. So that's one support resource, is all these jig circuits. Other support resources, there are reference designs available. When you go get your jobs and you want to go just get a reference design and not listen to someone like me talk, you just go to analog.com and you can get reference designs and just use those. That's all available. Then there's a users group available for LT Spice. LT Spice has, it's hosted on Yahoo. It's an independent users group. I don't read it. I'm just a happier person if I don't read it, But it actually, LT Spice is the only simulator with an independent users group. Most simulators have no users group. That's the normal situation. There's just not there aren't enough users of any given simulator to assemble a critical mass large enough to detonate the existence of a users group. That's the normal situation. If a users group exists, it's usually hosted as a forum on the website of the company that's selling that simulator in order to make it look like there's a large enough number of users collected to detonate the existence of have a critical mass large enough to detonate the existence of a users group. The only simulator with an independent users group started with nothing to do with me or anyone at Analog Devices is LT Spice. There's about 68,000 people there that can't live without 30 emails a day about LT Spice. People find that users group useful. Like I say, I don't follow it. I'm just a happier person if I don't read it. There are FAEs. There's even a huge Analog Devices presence here in the Philippines. You can get design support. When you get jobs in the industry and you want something designed, they'll just design the circuit for you. Don't even worry about a thing. And then this address here, that's my email address. If you have my calling card, that is the address on the card, and you don't have to write it down, because when you start LT Spice and you go help about, that's the address. That's that's how people reach me. That's how I can be reached. It turns out you can have millions of people using a piece of software that you use, and not that many people have questions about it. It's just a funny thing. There's not that many people want to know. Anyway. All right. Now we're going to get to, let's see what time it is. Okay, good. I promised I would tell you why current mode control is better than voltage mode. And now I'm going to talk about the whole feedback loop of a switch mode power supply. For many people, for people who are actually engineers working in industry, this is the most interesting stuff I talk about at all whatsoever. And this deals with the feedback loop of a switch mode power supply. Now, in this stuff, when you start talking about feedback loops and feedback theory, people immediately jump to the frequency domain and talk about transfer functions, and they go in this whole Bodhi plot thing. And here's a story. I'm sure you've all heard this recently. What you'd like to be able to do is look at the open loop transfer function. Have you had some feedback loop? If you're thinking of closing the loop on some feedback loop, don't close it yet. First, look at the open loop transfer function and look at how the phase changes as you increase the frequency. You want, and you want to roll off the gain so that the gain drops to below 0 dB before you acquire 180 degrees phase shift. Because if you have 180 degrees phase shift, you have positive feedback, which means ringing exponentially increases with time instead of decreases with time. But if you get this positive feedback only when the gain drops to below 0 dB, you're attenuating that, so you're good. That's the main thing you learn in stability analysis. All the rest is just a detail, really. That's the main idea. So let's rethink this. So let's do it first for something like an op-amp. This is the simplest circuit I can contrive that has a transfer function nominally like an op-amp. Okay? This is a transconductance, which means that the input is a voltage and the output is a current. The coefficient of transconductance is 1 million. So if I put a microvolt here, times a million is 1 amp. So that's what that element does. I read out that amp with this 1 ohm resistor, so that I put a microvolt there, I get an amp, I get a volt. The DC gain is 1 million, nominally like an op-amp. But I bypass that 1 ohm resistor with a capacitance of 0.159 farad, not microfarad, 1 over 2 pi farad. That'll put a 0 at 1 hertz, and that means you'll have a gain bandwidth of a million hertz. So it has a DC gain of 1 million and a gain bandwidth like 1 million. To round figures, nominally like an op-amp. Now, and over here I have the same circuit. Now, before I close the feedback loop around this thing, I want to know the transfer function. There's 2 ways of getting the transfer function. I can put a signal in the input, sweep the frequency, and plot the output. A direct method. I mean, that's extracting the transfer function of the circuit from the definition of what the transfer function is. A direct method. There's another way I could get it, though. I could take the input and the output, and I could just short them together. Short the input and the output together and perturb that short circuit with a voltage source, sweep the frequency, look at the ratio of these 2 voltages. I'm saying that this indirect method will give me the same as the direct method. Let's try it out. Okay, so here's the direct method, node Z. At DC, that is, a millihertz here, I have a gain of 120 dB. That's a gain of 1 million. Here's a pole at 1 hertz, and then it drops to 0 dB at a megahertz. So that's the transfer function we expect. Now let's look at this indirect ratio method. Okay, 120, it looks similar. You know what, let's overlay them. Yes, those are the same data. So I have 2 different ways of getting the same data, a direct method and an indirect method. All right, now, as engineers, we should prefer direct methods because they're less error prone. I mean, the whole difference between engineering and science is that engineering has to be correct. I mean, science doesn't have to be correct. You can say, well, we've got this hypothesis, we do an experiment, and we were wrong. It's all good. I mean, it's okay in science. Engineering doesn't work like that. Okay, it has to be correct. If you build a bridge and the bridge falls down because 1 million people, because there are 10,000 people on the bridge, well, we learned there were 10,000 people on the bridge and it falls. That's not the way it works. Should have been a scientist, not an engineer. So we should prefer direct methods because they're less error prone. So why am I talking about this? I mean, if you do this, it seems like the only value of doing that is you'll impress your classmates. It's clever or something. It's just like, what is the value of this? Well, the value of this will be clear when the situation changes. Say you don't have a circuit with a transfer function nominally like an op-amp. What if instead you actually have an op-amp? The direct method will not work. Because the op-amp has an offset voltage. If you take that offset voltage and multiply it by the DC gain, you have a number which is bigger than supply voltage. So the output is simply pegged at one rail or the other. Okay? However, if I take the input and output and short them together, use feedback to feedback means taking the input and output and shorting it together. So I configure it here as a voltage follower, put this voltage source in there, sweep the frequency, actually get the right number. Let's try this. So the indirect method gives me the right answer, and the direct method here, it has an error of about 60 dB. Well, 60 dB is not an error, it's just the wrong number, okay? It just doesn't work. All right, so there's something I want to point out here. But where I'm going to go with this is that I have, over the course of my life, fallen away from using frequency domain analysis for stability. That's what's happened to me. And the first thing I want to point out is that if you have a feedback loop, when you cut the feedback loop, the circuit doesn't work anymore. So to measure the transfer function, you have to solve the stability first. Then you can measure the open loop transfer function, and then you can say whether or not it's stable. That's not, you know, this doesn't bode well for a useful theory that you have to, I mean, the theory is supposed to help you solve stability, but you have to, the process for applying frequency domain analysis, first you solve the problem, then you get your data, then you can analyze whether or not your problem is solved. That's a problem, okay? And it's good, and I'm gonna hit it harder than just that, okay? Because the fact of the matter is, anytime you see a bunch of engineers having a spirited conversation of poles and zeros and stability and all that, if in that conversation is not how they are going to measure the open loop transfer function while the thing is operating closed loop, that discussion is just so much empty intellectualization, and I guarantee you, you will all encounter that discussion in your life. And that is all nonsense. That's just the deal. And I'm going to hit it harder than that, because this is actually what I'm known for, is I do things at a time domain, okay? Now, in a switchable power supply, the problem is even worse. The problem is, this circuit does not have a linear frequency domain analysis. It doesn't, there's no frequency domain description of this circuit. See, the thing is, okay, again, frequency domain analysis works for a linear system. If you have a linear system, all the frequencies are orthogonal. You can solve for the circuit one frequency at a time, and that is a correct way of looking at it. You can do that with correctness in a linear system. If you have a nonlinear system, then the frequencies are not orthogonal. They mix, and you can't solve it one frequency at a time. Now, you get some use out of linear analysis of nonlinear systems. Say you want to make a power audio amplifier. Before you apply a signal to it, the thing is, you know, just in equilibrium at a bias point. It acts as a linear circuit at that bias point, and you can do frequency domain analysis, and there would be some correctness to it. Of course, if you drive a signal, the transfer function changes very radically, and you will probably at some point in your life find a power amplifier that's stable at equilibrium, but if the output gets close to one rail or the other, the transfer function changes so much it starts oscillating. You'll probably see one like that in your life at some point. But, you know, people still apply linear. I mean, the real reason why stability is done in the frequency domain and linear analysis is because it's the only thing you can do in a classroom with algebra. It's not because it's correct. That's the reason. And if you if you look at it any other way, you don't see what's happening. Now the thing is, this is not a linear circuit. This switch is fully on or fully off. They don't just mix frequencies, they mix frequencies as much as possible. And that's not even the worst of it. The worst of it is that flip-flop. There's absolutely no frequency domain description for flip-flop. So there is no frequency domain description of this circuit. There just isn't. Okay, now, you will find people looking at this in the frequency domain, and the reason why you get people looking at the frequency domain is because they can't understand the linear circuit. They say, okay, what we'll do is we'll get everyone in the design review meeting to agree to only discuss frequencies well below the switching frequency. And then you can build the linearized model of this thing. Because well below the switching frequency, you can. And here's actually how you can extract that low frequency behavior here. What you do, okay, to extract the transfer function, you run a sine wave in the time domain. And here you can see you want to look at the ratio of voltages to either side of this voltage source inserted in the feedback path. And you can see the high frequency is the switching. And if you look at these envelopes of the perturbation, it looks like a sine wave in, sine wave out, exactly like a linear circuit at that lower frequency. And you can again see, yes, there is a shift in gain and a shift in phase. And that shift in gain and phase is the open loop transfer function at that perturbation frequency. And you can quantitate that with Fourier analysis. Here, right click, view, FFT, we plot the ratio, and we look at the phase shift at the perturbation frequency. You get the transfer function as 9.7 dB in 46 degrees. That's the linear behavior of that circuit. That actually is the linear behavior of the circuit. That's all fine. It's basically 1 point of the Bode plot. And if you change the perturbation frequency, rerun the simulation, redo the FFT, redo the ratio, and then query that new frequency bin, you get 1 more point of the Bode plot. With a great deal of effort and work and time, you can extract the small signal behavior of the circuit, and it has a level of correctness at low frequencies. Okay. Now, that's a lot of work and a lot of time. The work I can automate. You can write a program in LTSpice you can write a program that runs on your simulated data. You do this with something called dot measure statements, and you can write a program that does the Fourier transform and looks at the ratio, report you the gain, magnitude, and phase. And then you can step it. Now the simulation takes a long time, but I'll just take a real simple system. And this little program of dot measure statements will report the gain, magnitude, and phase. And then every one of these simulations is 1 point of the Bode plot, and I've scanned from 1/10 of a hertz to 10 megahertz. And as you zoom in here, I've scanned so many, I've stepped over so many decades of frequency, it looks like I'm meandering down into a fractal pattern. But every one of these waveforms is going to be 1 point of the Bode plot. The output of the error statements are in the error log, and that is my Bode data. And this can be plotted, okay? See, the thing is, each dot measure, okay, if you right click, there's a menu command called plot dot step dot measure data. Here's the thing. If you write a dot measure statement, the output is a number, as in a scalar number. It's one number. If you also do dot step, like I did for the feed forward cap, then you have a set of simulations. You have this one number over the set of simulations that you can plot. So if you have both dot step and dot measure in the same simulation, then this menu command will not be grayed out, and you can plot the open loop transfer function. So this technique extracts the frequency domain response from time domain data, and this method is called frequency response analysis. This is the mathematics behind instruments like a Venable or Bode 100. There's a few other commercial instruments that will extract this from. Okay, great. Many people love to do this, and you can do this for a switch mode power supply, and many people like to do that, and that makes them happy, and I'm happy for them. However, I never do. I really never look at a peak current mode buck in the frequency domain, and the reason I don't is because I can't accomplish anything with it. Okay, I mean, not only is it not particularly valid, you really can't. You won't change the design when you're done. Here's the thing. Where frequency domain analysis has gotten some traction, has become popular, and is canonized in our study is what we should know about. It's useful if the situation goes like this. Say you go all the way around the feedback loop and you find which component values give rise to the poles and zeros. Okay, so you can do that. Then you might think of a strategy where you will change a component value to move a zero to cancel a pole to make the thing stable. That's really useful. That would be useful. And that is exactly what is entirely impossible in a current mode buck. Let's go all the way around the feedback loop and find all the poles and zeros. And I will start with this node here. This is the ITH node. This is the switch node. I'll go all the way around the ITH node back to this voltage here. Okay? Now, we got everyone to agree to look at only low frequencies. So if you look at very low frequencies, this voltage controls the peak current. So, that means that this voltage changes the current. Okay? That's what it means. And that means that all of this is just a transconductance. There's the switch node, here's the ITH. Because this voltage changes the current out of the switch. And you can, that's all it is. You can verify that by putting a voltage source here and here, changing this voltage, you see the current through the voltage changes. But it's easier to get than that because very simply, since this voltage, it's just transconductance. Usually the transconductance is equal to the current output of the power supply, maximum current, because typically you have 1 volt active region here, so 0 to 1 volt here is 0 to full scale current. So you have a 5 amp power supply, the transconductance is usually 5, because you typically have 1 volt active region. But all of that is a transconductance, okay? Y'all with me? Smile. I needed some smiles. It's been a long day for me. Good, that's what I like. Alrighty, now, the rest of this circuit is all a linear circuit. So we can use our normal electrical engineering knowledge, analytical ability, and intuition to understand the rest of the circuit. So let's do that. Okay, so from here to here is a transconductance. Now we have an inductor. What phase shift does the inductor cause? Do we have an electrical engineer in the room? Oh, come on. You're going to look at me like, what phase shift does the inductor cause? Oh, cowards. Such cowards. Such cowardice. Oh, my God. How about remote site? What phase shift does this inductor cause? I've lost them an hour ago. So you want me to tell you. I just want to be clear on this. You want me to tell you the phase shift from the inductor. Is that what you want? You're all on board with me just telling you what the phase shift from the inductor is? I want to know. Did I hear you say something? Huh? She says 90 degrees. Who agrees with her? Yes! How many people agree? There we are. That's yes. You know what this reminds me of? The penguins. Think about the penguins. Now, penguins are actually mostly tropical birds, believe it or not. They're mostly in warm climates. But we're familiar, they're all in the southern hemisphere, but mostly in warm areas. But I'm going to talk about the Antarctic penguin. You know, think of their lives. They're walking around the ice, and they find a hole in the ice. What do they want to do? They want to jump in the hole, you know, because they want to fish and play, right? That's what they want to do. But there's a danger. There could be leopard seal or orca. And those animals eat penguin, which is quite singularly bad if you are a penguin. So here's the dilemma you're in. You find a hole in the ice, you want to jump in the hole and play and fish, but you could get eaten. Well, penguin society has developed to handle this situation. If they didn't figure out how to handle this situation, there wouldn't be any penguin. So what do? They look at the hole in the ice, and they don't jump in. They immediately stand back as they recognize the danger. And they kind of like realize that they want to play, and they, you know, kind of play around the hole a little bit. They get comfortable, relax, and this will go on for a while. And eventually, one of them will fall into the water. And everybody's gasped and steps back, and they wait. And penguin can hold their breath for a long time. So it could be a wait. And they'll stand and wait. And after a while, the penguin will come up. He's got a fish in his mouth. He makes happy sounds, and they all jump in and they have a good time. That's exactly what just happened. See, I said, what's the phase shift from the inductor? You all recognize the danger, silence, right? Just exactly the same thing. Then one person said, you know, got him a little looser, more comfortable. Eventually they said, oh, it's 90 degrees. And they all said, yep, it's 90 degrees. And there, it's exactly like the penguin with one difference, and that is this time there is an orca, and he eats the penguin, because the answer is not 90 degrees. The answer is 0. See, this is a transconductance from here to here. This is a current. It's either a current or it is not. If you put something with a finite impedance in series with something with an infinite impedance, you don't cause a phase shift. You're regulating a current through the inductor. And that is the whole point to current mode control. See, that's why it's better, is because this circuit regulates current through the inductor. That's what it's doing, so the inductor doesn't cause a phase shift. That's what's happening. That's why current mode is better than voltage mode. Okay. Was that fun? A little bit? Good. Now let's continue through the feedback loop. All right. So current comes through something in series with a current. Yeah, it's other current. It's not solely current here. Now on the output, we have this capacitor ground. Disco! We found something that can cause a phase shift. We found one pole. Maybe we can do something with small signal linear analysis like they taught we would always want to use in school, right? That is one pole. Let's continue. All right, the output divided down. We compared the divided version of the output to the reference voltage. Difference between the divided version of the output and the reference voltage is the error voltage, which is amplified to be a current flowing out the pin where we started. However, it is not the current flowing out of the error amplifier that sets the peak inductor current. It is the voltage on the output of the error amplifier that sets the peak inductor current. So to complete going around the feedback loop, we have to read out this current to a voltage. Well, if you've got current and you need voltage, you could read it out with a resistor. That would be problematic. In principle, you could get it to work. But let me just cut to the chase. A much better idea would be to read out that current to a voltage with a capacitor. Because if you convert current to voltage with a capacitor, you're going to have a huge gain at DC. And the tightness of regulation of a negative feedback loop increases as the ratio of open loop to closed loop gain increases. That capacitor gives you a huge, AVOL, a huge DC gain. And the reason why that's a voltage is because that's a capacitor. And that is one more pole. Okay. So we've gone all the way around the feedback loop. We've found two poles. Each pole can get you up to infinitesimally close to 90 degrees phase shift. Two poles can get you up to infinitesimally close to 180 degrees phase shift, up to infinitesimally close to phase reversal, up to infinitesimally close to oscillating. It can't oscillate, but you are up to infinitesimally close to oscillating. So if there's any other phase shift in the system, like a delay, like this part here, okay? This part converts that voltage to a current coming out of the switches. That's actually why you buy that part, because it does that. And when it does that, it's got to have some delay. So you might think, you've gone around the feedback loop and we have two poles and some delay. Well, if you think of this feedback loop as two poles and some delay, I think a reasonable person would be inclined to think that if you did not do a small signal linear analysis of this feedback loop for stability, if you didn't do that, you weren't being a responsible adult. Well, if you thought that, you'd be wrong. Because I skipped some things when I went around the feedback loop. First of all, this capacitor will have ESR, that is a 0. And see this capacitor? We buy that capacitor, that resistor, that is another 0. The transfer function is actually two poles and two zeros, which means that it is not remotely close to oscillating. But what about that delay? The delay could mess up any feedback loop. Well, it turns out that when you got the design review meeting to agree to only discuss frequencies well below the switching frequencies, because you couldn't analyze the nonlinear part of the circuit, then so it's the only thing you could analyze. That's not nearly enough. You have to, if you actually analyze the circuit correctly, that is in the time domain with all the nonlinear stuff to it, then it turns out you have to roll off the transfer function well below the Nyquist frequency, not well below the switching frequency. That's a very low frequency indeed. That delay is negligible. That means this feedback loop is two poles and two zeros, and that means it's stable. I can't make equations for component values if it's stable for all values. Now, what's the limit for that picture to be correct? Limit is that it's possible to look at in the frequency domain, which means that you roll off the transfer function well below the Nyquist frequency. So as soon as you look at this problem below the Nyquist frequency, you've thrown away where the stability problems are. That's why I don't do anything with small signal linear analysis on a current lock controller. It's meaningless. It has no value. You can do it. You can look at all this Bode plots, you can do all this frequency response analysis. You'll never improve a design if you look at it like that. That's the problem. Okay, now, if you know that, you can have a full, long, rich, profitable life designing switch mode power supplies. You'll be way ahead of most people you'll meet. Okay. I've done it. You can do it. It's easy. And you will really understand these switch power supplies. Now, you'll end up with a couple things you have to be concerned about. One is that, okay, well, it's correct in practice, but it's not exact academically. This pole, so far I've gone around the feedback loop twice. First time I said it's 2 poles and some delay. I said, oh no, that's not true. It's actually 2 poles and some zeros and no delay. That in practice is you can run with that. That's good, that's good. That's the way power supplies actually work. They're actually 2 poles and 2 zeros and no delay. That's the way they actually work, all of them. But it's not exactly correct. And the reason why it's not exactly correct is slope compensation. Slope compensation changes the story a little bit. See, the thing is, if I reset this flip-flop not according to inductor current, but current plus something else, the dimensions of current plus something else is not current. And if I reset this flip-flop according to a quantity that is not current from dimensional analysis alone, I know that the transfer function from there to there is not a transconductance. It has to be something else. Okay? Now, what it actually is there's some impedance here. Not much, basically negligible, but you should be aware that that would then make it exact if you had the right impedance to put there. And that is where you get into these proprietary slope compensation functions. I said that in analog devices, we don't use triangular ramps. Basically this triangular function here, it avoids a high frequency instability due to all the nonlinear waveforms going on, something that's a little quite outside of frequency domain analysis. That's the thing it's solving. People try to transcribe that to frequency domain analysis so you can do Bode plots and that stability, but it's really just nonsense. You should just look at it in the time domain. It's much more straightforward. But anyway, you want to add as little of slope as possible so that you can avoid the high frequency stability, but not so much that you mess up the low frequency stability. So what you want to do is you want to have a function. Okay, see, the amount of slope that you need depends on the duty cycle. Let's make a plot of what slope to use versus duty cycle. So this is slope. That's the slope of this function. M will be the slope, and this will be the duty cycle. That is 100% duty cycle, that's 50% duty cycle. Now, if you're below 50% duty cycle, zero slope's okay, you don't need it. If you're at a high duty cycle, you do need slope. Okay, now you can solve for, a number of people have solved for the function that connects those two dots. I've done it, a number of other people have done it. And when you're done, it looks more like a straight line than I can draw on this piece of paper. Okay, so that's the slope versus duty. So the slope function should look quadratic. And that's where you see those quadratic curves on data sheets. Fact of the matter is, once you're using analog devices controller with this proprietary slope compensation function, your stability problem is solved for all component values. That's my story. I'm sticking to it. That's the truth. In all rigor. Okay, now that's the deal with the current mode controller. In a current mode controller, people do analyze these things in the Bode. I realize that since you're fresh out of, since you're right in the middle of it all, and you're actually listening to these classes talking about frequency domain analysis, you probably wonder, why am I saying it's totally useless? And you realize, man, you must have really gotten into a lot of trouble over this. I mean, standing up in front of a bunch of electrical engineers and telling them Bode plots are nonsense. I mean, it's like I must have some kind of a death wish or something, you know. I mean, people will look at me like, and they'll say, he's a witch. He's a witch. Throw him in water, see if he floats. You know, it's like, so let me put a little bit of context on this. Where did this, canonized doctrine that you have to look at this in the frequency domain came from? It really came from this, because the story over here is very different. See, in a voltage mode controller, this voltage controls the duty cycle, so the transfer function from here to here is basically a voltage gain. And the voltage gain is basically the input voltage divided by this peak-to-peak amplitude here. Because this is 1 volt peak to peak, you have 12 volts in, you go 0 to 12 volts from 0 to 1 volt here. Okay, so that's your voltage gain. So this is now an E source, not a G source. And if that's a voltage, then that's a pole, and that's a pole. And the answer regarding stability of a feedback loop with 3 poles is that it oscillates. unless you have contrived it not to, either by inserting a zero to cancel pole or by making one pole at such a low frequency you go through crossover before the other poles cause phase shift. That's the deal. And basically, you know, in the 1970s, I don't know the number, I'm guessing there were probably only 50 people in the United States that could look at this at a small signal response and make this thing stable. So when someone said, look, I've had enough of that, let's buy a flip-flop, solve this problem once and forever. You know, obviously these 50 people who are used to being the high priests and switchboard power supplies, they're still going to analyze it with frequency domain. They're still going to look at it in the frequency domain. That's where a lot of it comes from. But I've actually fallen very far away from frequency domain analysis for almost every circuit. I really do see frequency domain analysis as something that you do when you don't have a computer. You know, it's not, you'd only do if the only thing you can do is algebra, you might get a signal out of it, and you might be able to placate somebody that you understand the circuit with that. I don't see any other use for it. So let's rethink the whole thing. Let's go back to the Bode plot. Here I have the same op amp here. See, a mega ohm, an ohm, and 1/2 pi farad. That's my gain of 1,000,000, 1 megahertz gain bandwidth, but I'm going to put 2 other poles in the thing. Okay, let's look at this transfer function. Okay, now I'm going to attach a cursor to the phase plot here. Now in a Bode plot, I use solid for magnitude and dashed line as the phase. Now every time you see a Bode plot, the first thing you have to do is you'll have to look at the phase shift at DC, because there's 2 conventions for plotting Bode plots. Neither is right or wrong, both are used. The phase shift at 0 is either 0 or it's 180. Depends on whether you decided the inverting or non-inverting input. You need to know which Bode plot you're looking at so you know how to apply the Bode condition, because you don't want to see more than 180 degrees phase shift before you go through crossover, and so you need to know what phase shift was 0. This, at 0 hertz, I put this cursor here so I can read out it was 0 degrees. Now I know the Bode condition. I can't get 180 degrees phase shift before the gain drops to 0 dB. So let's increase frequency and see how the shift goes. Okay, higher frequency, higher frequency. There's 120 degrees phase shift, so that if it went crossover at that point, the phase margin would be 60 degrees, which many people feel is a happy number, but oh no, I got lots of gain at that frequency. Let's continue. Here's 160 degrees phase shift. That means I would have 20 degrees phase margin if it went through crossover. It's not near crossover. Here, let's go up here. 175 degrees. I would only have 5 degrees phase margin if it went through. I still have a huge gain. And look, it just goes straight through. That's positive feedback, and it keeps phase shifting. This thing would not meet the Bode condition. So let me ask you, can I use this op amp in a unity gain? Are we going to play penguins again? You say no? How many people say yes? How many people say no? It would not have phase margin if I closed that unity gain. I've tortured you enough. Let's just do it. Actually, there's only one way of telling if this is stable in the time domain. There's actually only one way, and that is by doing the simulation in the time domain. There actually is no other test for stability than simulating in the time domain. So let's do it. Let's take the inverting input, connect it to the output, unground that. Now it's a voltage follower. I will comment out the frequency domain, run it in the time domain, and there's the output, there's the input. It's perfectly stable. It has no phase margin. Interesting. See, the Bode condition is a sufficient condition for stability, but it is not a necessary condition for stability. So this does not meet the Bode condition. It's perfectly stable. In fact, it's even a common circuit. In the 70s and 80s, there were op amps that had thermal time constants that would cause phase shifts. So you could have phase reversal at 100 hertz or kilohertz. You'd still have enough gain that it would still be stable there. In fact, here's the thing. And here's, if so from just a top-level philosophical point of view, one problem with frequency domain analysis is that you have to solve the stability before you apply the theory, and that's really bad. But it's not only that, it's worse than that. See, the thing is, stability is much easier to understand in the time domain from a feedback point of view. Because, if you want to make something an oscillator with feedback, look at it in the time domain. If you put a signal in the amplifier, if the output of the amplifier looks exactly like what you put into it, well, if you take the input and out and connect it together, it could just run forever. That's an easy to understand time domain picture of stability, and that picture is correct. And you can apply it here to understand why this is stable. Yes, it has the wrong phase, but it's been amplified so much it can't recognize the output as the input, and that's why it's stable. Now, there's an interesting thing. If you transcribe this correct time domain picture to the frequency domain, for something to oscillate, the phase shift has to be exactly 0 and exactly 0 dB gain shift, or it cannot oscillate. Okay, that's the way you transcribe it. And the problem with that is a real circuit can't have exactly 0 dB gain shift unless it has automatic gain control, which means it is not a linear circuit. That's a problem. You're studying stability with linear analysis, but a linear circuit cannot oscillate. That's a problem. Oh, but there's more. I mean, look at this circuit. Okay, here we have a feedback loop. Okay, see, here's the feedback loop. The signal goes in here, here's an output, goes in here. This is a feedback loop here. Now, if you analyze that feedback loop, the circuit is stable. It meets the Bode condition. You can prove this circuit is stable if you analyze that feedback loop. But the circuit oscillates. And the reason why it does, the feedback loop has nothing to do with the oscillation. The feedback loop is developing negative resistance between these two terminals. You put it at the one end of the transmission line, mismatch the other end, you just have this reflection dialing back and forth. And that's actually, you should probably realize that most oscillators aren't feedback oscillators. I mean, except for a crystal or an LC circuit. I mean, you're usually charging and discharging a cap or a transmission line oscillator. So basically, I have, the older I get, the more I've gotten away from doing frequency domain analysis. And for stability, it's gone. I no longer use it at all. Now, I've shown you intellectual arguments and proofs and all this stuff. And for a switch mode power supply, there's nothing you can do. You've thrown away what the stability problems are in this current mode controller if you look at it in the frequency domain. That's all fine. But there's actually a reason why I don't do stability analysis in the frequency domain. I haven't told you the actual reason yet. The actual reason why I don't do it is because I know a lot of electrical engineers that I consider are much better electrical engineers than me. These are IC designers. People like my boss, Robert Dobkin, founder of the company I work for, okay? These people know circuit design better than me. And they stopped doing stability analysis in the frequency, and they stopped doing stability analysis for their circuits 30 years ago. And the reason is they're designing integrated circuits, and there's no way you can cut every feedback loop of an integrated circuit, spend 10 minutes on every Bode plot, and decide whether or not it's stable. There is one and only one way of telling whether or not an integrated circuit is stable, and that is to do a time domain analysis of that circuit and see if anything buzzes. And that's been the design technique for 30 years. That's why I don't do it for stability analysis. Just what it is. So is that fun? That's actually what people listen to me for. That's why, was that fun? Good. All right. Sorry about the penguin joke. Okay. I mean, it was a big enough point of why current mode is better. I had to spend some time so it would envelop it. That's the reason. Okay. Okay. Good. I'm not going to talk. Let's see. 3 o'clock. When are you supposed to take a break? 3 o'clock. All right. Let's take a little break now, and then we'll go through a few more things. I probably won't talk a lot about this numerical analysis. You're going to have a paper version of it. I'll put just a 5-10 minutes word on that. Also, a lot of people just aren't interested in this numerical methods. If you don't do numerical methods for a living, it's what I do, but I find it usually doesn't work much because I'm the guy that thought all this stuff, and it's just too memey. It's just not good. It doesn't really work in a presentation, so we'll just cut it short. All right, let's have a break.
Please be back at 3:30.
How you doing?
Alam kaya nila. Narinig kaya nila. Yeah. Hi. Okay, good. I mean, it will come very soon. 32 dash. Okay, kaya break na is 30 kilos. Can't break the sauce. I know. I mean, that's amazing. That's the solution. Plus, of course. Yeah, of course. So now we're